So this is the Advanced Steel class number 29 and 2020 April, and this is the 22nd. A lot of number 2 and the number 4, which is the 2 square. Well, okay, so this is going to be the last class that the content might be used in the final examination. At the end of this class, we shall talk about it, and I can arrange a Zoom meeting if you want, but I don't know what will be the what's gonna be the key points to talk about in the Zoom. I'm not sure if the discussion is needed. Alright, anyway, well, it can be done. So we are going to come back to where we left off yesterday, and we stopped somewhere before the torsional bracing yesterday. So the torsional bracing, it is another part for the beam bracing, as the beam, when it fell by the stability, it fails by the lateral torsional buckling, and that lateral torsional buckling, that means your brace can be the lateral brace, and you also need the torsional brace to suppress the torsion mode. Okay, so the lateral part was already discussed, and we know very well that the lateral brace is helping the, let me move my microphone a little bit. It's helping the compression flange such that it mobilizes the full compression force at the, and that is going to cause to enable the beam to mobilize the full moment as you wish. So the lateral brace is attached to the compression flange. If you put the brace at the wrong point, then it is useless. That's the key idea for the key requirement for the lateral brace. But now we are gonna talk about the torsional brace, and I think something like this, I might look into this information and bring it to you all next year, in the next year lectures, or if I by chance do something, look into this matter in a little bit later, then okay, you might be able to watch it soon. But it's just up to the schedule, but the worst thing should be in the next year, because this is the beauty of the online teaching, and not only just the online teaching, but it is about the video class video recording, because the content that is already covered, it shouldn't be covered again. It is just a waste of my time to do things like repeatedly, but instead of doing it that way, I just go for something new and something that we cannot afford to do in the 27 to 30 classes time that we have in one semester. When we subtract the holidays and so on and so forth, then we have effectively around 27 to 30 classes. It is written that 30 classes, right? But many times we get disturbed. The schedule is disturbed by the holiday and events. So the point like this could be pick up. I think it should be very interesting to pick up, to be picked up, and I think that you guys signed up for the higher education, the master education, because you want to learn. You may not just want to pass the examination. So learning is supposed to be lifelong, and probably you have the interest in coming back and see why this one is usable, why is it good enough. Anyhow, the equations of the critical moment that incorporates the brace, which is the lateral, not lateral brace anymore this time, it is the torsional brace, is given over here, and you have the M naught, which adds up with this part. This part here, well, first of all, M naught is from what? M naught is from the section that is not braced. So you have the section, and you know the this thing from the derivation we used to see that you do not have the brace along the span, and you have the uniform moment acting on the beam, and then you allow the lateral torsional buckling to occur. So you're gonna expect the CB, you're gonna expect the other things that coming in back in here later. And this part here is equipped, okay, it is enhanced by this which represents the torsional bracing. So this torsional brace stiffness, it comes along with the EIY. IY is the lateral bending stiffness of the beam of the girder, right? It is not the major axis. This is the minor axis stiffness. Okay, so it is the first part, and equipped, enhanced by the brace part. And well, the study has been conducted. By the way, this beta B is given by the how to say? It is the uniform rotational spring applied along the beam. It is not just going on at a particular point. All right. This is just a simplification, because you know already that it is difficult enough to end up with the M naught, and that we require. We use the assumption that the moment is uniform, whereas in reality it is not, and then we have the CB factor. And likewise, in this case, when you apply the spring, the rotational spring, this rotational spring is simplified. It is just how to say, just distributed along the length of the beam. Okay, all right. And the analysis by the finite element is given BASP here. Actually, Yurav talks about the BASP somewhere. I'm not sure if it is in this paper or not, but it was supposed to be in this paper. He talks about the BASP, which is a finite element software that incorporates the buckling of the as the beam is constructed from the shell, right? Okay, all cases considered were solved using elastic finite element program. Well, I think the elastic is one keyword. All cases considered were solved using elastic finite element program. Identify as BASP in figures. Okay, whatever. These people should be the set of a group of people who develop the program. The solution and the design recommendations presented are consistent with the work of other Kirby Nethercutt. Okay, whatever. All right. Okay, so BASP is the program, but what I want to just emphasize, and again buckling analysis was carried out from the BASP. That's why you can get this point, this line, these results we have. So first of all, we have the let's see a bit about the explanation. The dash shown by the dot dash line in figure 19, which is this one. So the solid line are finite elements result with no stiffener, okay, at the different spans, solid line, alright. And under uniform moment with brace attached to the compression flange, cross-section distortion caused by poor correlation between causes the poor correlation, okay, between BASP and equation number 5. Shorter cross-section distortion could be handled by using effective brace stiffness. So over here, the BASP, okay, the equation 5 is the equation above here, okay, and this equation above here cannot account for the distortion, okay. So what is the distortion, cross-sectional distortion? Well, the point for this graph is to address the needs of the stiffener that prevents the distortion. Actually, the stiffener are used in many occasions. First of all, this when the beam buckles from the lateral torsional buckling, okay, the beam turns into the red shape. The red shape is the distorted shape. It's not enough space. Distorted shape. So, well, you can expect that there will be the twisting force, twisting moment that's gonna cause the cross section under the bracing condition. You're gonna end up with some distortion of the cross section. So the cross section is deformable, and without the stiffener, you end up with this. And the equation above here simply cannot account for this distortion, because the behavior like this is localized, and it is varying along the length. So as the closed form solution does not incorporate this fact, that means equation 5 is greater than the analysis which is carried out by the finite element software, and that equation number 6. Well, the equation number 6 is going to incorporate the fact about the distortion, but okay, without distortion, you'll be getting this is for all lengths, so it is very far from there, less far, and over here. Okay. So let me just note it down, like the importance. This is to show the importance of the stiffener that prevent distortion. Okay. So next. So the torsional stiffness and the spring stiffness, the brace stiffness, again, that is used against the torsion, going to be examined. Basically, when we look at the system of the beam and the brace and torsional brace, you have many, like a spring system. Let me explain you this way. So it is like the spring system connecting together. For example, you have the brace, the part which is the diaphragm. Sometimes we call the diaphragm, or this part here has its own stiffness. The girder itself, it has its own stiffness in bending. Okay, the girder can be bent about the axis which is coming out of plane. So the bend shape is going to look pretty much like this. This part also contribute to the torsional stiffness of the overall system, right? The cross sections, so the B section is going to be there, the brace itself is going to be there, the girder effect is going to be there. So as you have so many springs, let's say, and these many springs are attached like here. If you think of the linear spring, if the explanation is on the rotational spring, I think it might be difficult for you to see. But if I come up with the linear spring and then I call it beta 1, beta 2, beta 3, I don't know why. What is the intention of changing from the K to the beta? I got to go ask Yura. But okay, now we want to get the overall, the system beta. So if this is going to be represented by one spring system like this, and which is to be called the beta T, total stiffness. So what is it going to be? So if you apply the force, right? The first spring is going to contribute like the delta 1, delta 2, and delta 3. How is delta 1 calculated? Delta 1 is calculated by, it is calculated from F over beta 1, right? And for delta 2, likewise, F over beta 2 and F over beta 3. If you want to find the overall stiffness of the system like that, the overall system stiffness is going to produce the delta T. Okay, so F over beta T is delta T, and delta T is the summation of delta 1 plus delta 2 plus delta 3. So the total is equals to this add up with this, add up with this. By chance, we know that F are the same thing. So you're going to have 1 over beta 1, 1 over beta 2, 1 over beta equals to 1 over beta T, which is here. Okay. Right. So that's why the way the total stiffness of the system is computed is not just the sum of beta. That will be the parallel system. So if you have the system like this, okay, and then you want to find the spring stiffness equivalent, if the spring are attached in a parallel configuration like this, then you sum them up. But it is different. It is put in order like this. So you get this total stiffness first computed from here. So let's talk about the beta B, this part here first. This is the brace contribution from the this is the brace itself, the contribution from the brace. So the brace stiffness, how is it calculated? As it is the brace against the rotation, so basically it is the moment divided by the angle of twist, or the radian unit, right, of the theta angle of twist, which is something like this. So you have the moment part and the angle of twist. It is just a simple way to find the stiffness, but Yura has prepared sets of formulas for the calculation of stiffness of each kind. For example, the first kind, if you are dealing with the girder here, and these two girders are under, well, the deck. So the concrete deck or steel deck or something that connects the top flange of the girder together, that means at the construction, the distance between two girder is D, and when the girder when it fails, the distance D is going to be maintained, because the diaphragm is going to connect and lock and prevent the two top flanges from going away from each other independently. Okay, they must move together. Right, so that's one system, and with that restraining effect from the diaphragm, you end up with this double curvature shape of the brace, and this is the brace that is made of just the steel beam, okay, and connects by the plate between two webs. Okay, now if the torsional brace is given by the beam as well, but it is the different situation. This is the through girder situation. So what is this through girder? This through girder is situations that you actually can Google up, but just to make it quick for this course here, you might see many bridges which is made of the steel girder, and platform for the traffic. Generally, this is used for the rail, the rail system, for the railway. So the train is going to run like this on the rail, and this is the platform that carries the load. So this is called the through girder system. It is used like the side barrier. Fine. So for this configuration, when as you do not have any restraining, displacement restraining, anything that controls the relative displacement between two top flanges, so you end up with this shape. It's gonna form only single curvature, and you know that the single curvature is more well, it is easier to form than the double curvature, and from this, that makes the stiffness of the brace lower than the other case that the double curvature could be formed. So that makes like 3 times difference in the stiffness. And this is just for some situations that the above is the situation where you have the girder as the rotational or torsional brace, but in many situations you have something so-called diaphragm. and this diaphragm is somewhere here. So this is your girder. Actually, it's not going to be that high. And you have the diaphragm. If you commute around Bangkok area or whichever area, in fact, whichever area, and when you are under the flyover, and if the flyover is a steel structure, it's a steel bridge, you're gonna see the steel girder, and the steel girder generally, at least for you're gonna see the diaphragm at a few locations like this. So the diaphragm, this is a girder, and this is a diaphragm. So diaphragm just locks girders together, and that enhance the capacity, that enhance the stability, and you can see many shapes of the diaphragm. So diaphragm could be the tension system diaphragm, it could be the compression system diaphragm, or the K-brace system. And for a tension system, you must have 1, 2, 3. You must have these 3 components. Here is going to be connected to the girder, right? So for a tension system, since the tension element is much stiffer than the compression, so compression element is suspected that it will buckle. So we make use of just one in the calculation. Well, in reality, this compression is going to participate, and that's gonna enhance the capacity. It's gonna enhance the stiffness of the torsional brace, but we may not just count it in for simplicity. So three members gonna be needed. This one is crucial. It is necessary. Okay. Next system, you have compression. So both of them are under compression. You don't have the horizontal one, so you cannot. You might not form the tension elements. So this is going to be more expensive because member under compression is going to be more expensive. And the K-brace, so you have the horizontal one and one under tension, another under compression. So yeah, up to you, up to the limitation from other point of view. And right now we look into this, just the side, on the side of the system. You see that the beta B is already given. So the beta B is the torsional stiffness, rotational stiffness, which is computed from the moment divided by the theta. Theta is what? Theta is approximate from here. So the lateral displacement that you expect, that will be from the calculation divided by the height of the beam of the girder. So this constitute the shear, the torsion, not the torsion, the angle, the rotation. So you get the moment divided by the angle of rotation, you get the torsional stiffness of the diaphragm. Okay. And right now we enlisted 3 parameters with 3 torsional spring stiffness already. The first one, which is the beta subscript B for the brace, is already covered. Then we have the remaining 2, which are the section, the deformability of the section that reduce the torsional brace stiffness, and the beta G, which is the girder stiffness, that also participate in the rotational stiffness of the brace. So let's see. I'm not sure if I have uploaded this paper or not, but actually it's not difficult to find. Anyway, I put it there if I find that not available there yet. So this one here, it talks about the diaphragm, frame, blah blah blah. But the thing is that I will not read it for you because you can read it back home. The thing is that when you have the two girder connected to each other, and when these two brace against the torsion like this, the torsional brace is going to produce the moment, right? Because it restrain your beam against the rotation. So of course that restraining effect is going to cause the moment. So the bracing moment, if you calculate, you will find that there will be something that counteract with this MBR, the bracing moment. So the MBR will be computed from the beam, computed from the diaphragm. You can compute the MBR quite easily. You get MBR. Total moment is 2 MBR. Now you need to balance, you need to equilibrate the system here, right? Because if you have the moment, that means you need the counteracting moment, and the counteracting moment is going to be from the resistance of the girder. So this moment is going to cause you this pair of force couple. So you have 2 MBR, and the force required or the force that is caused on the girder itself is going to be 2 MBR divided by S, where the S is the spacing between two girders. The point is that the explanation in the paper here is not so detailed, so I'm gonna explain you. The point is that here you have the point force acting, which is the point force that is caused by the brace, the torsional brace. So it is the 2 MBR over S. Your beam has the stiffness, and that is going to make your beam deform like this. In order to find the deformation here, well, let's call the deformation the delta. If I want to call this one P, just to make it simple first, what is the relationship between this P and the deflection delta? You can just do this on the back of the envelope or just on the scratch pad, right? It is the PL cube over 48 EI, or just Google up. So the deflection is computed from the force. You have the reactions, and you can get the bending moment diagram. You compute everything accordingly, and then you get the delta equals to PL cube over 48 EI. Well, the E is simple. We do not need any judgment for the E, because we are talking about steel structure, so it is simple. It is just the E steel. But what about the I? I was supposed to be which I? IX or IY? this deflection here is controlled by the IX strong axis, right? We are not talking about the lateral, not the horizontal deflection. We are talking about the vertical deflection, and the vertical deflection is controlled by IX. Okay, so just to make sure, because when we are in this course, we deal with lateral deflection, vertical deflections. So you got to just stay tuned and make sure that you understand how the mechanism, how it works, and why the formulation goes this way. All right. So now I have the delta. I will just rewrite the P in terms of delta. So I have the 48 EIX over L cube, and that is multiplied by the delta equals to P. Am I right? Get this move up there, get this move down there. So 48 EI over L cube multiplied by delta equals to P. The thing is that the P is equals to 2 times of MBR over S. So this is going to be replaced by 2 times, I will say that it is equals to 2 MBR over S, where S is a spacing between two girders. Okay. Now, what next? It is not shown in here. It is not covered in detail why this formula comes up. Just the explanation that I think it is too difficult many times for people who read. Okay, so I spent some time looking at it, and well, we were gonna see how it ends up at 12 EI S square over L cube. Now we come here. This picture, okay, actually it is pretty much like this one, but I redraw it. So the effects from the MBR cause the downward force on one girder and the upward force on another, and that means they are the equal amount of force, as you can see as I wrote it down this way. Same magnitude of force, same magnitude of deflection, but one is the upward deflection and another is the downward deflection. So basically, if I want to find the relative deflections between two girder, here is how much? Delta and delta, right? 1 plus 1 minus, so it turns out to be 2 delta. This is the total relative deformation between two. Or if you want to get the angle, so the angle could be computed. And this is to be called theta. And theta is computed from, it is a little too small. theta is computed from 2 delta, right, divided by the S. Okay. Now this angle of distortion is given by theta. Now we come back here. We take the M. We will present the M in terms of the rotational, the torsional stiffness multiplied by the theta. Okay. So we have the 2 over S, which is still there. And then MBR is given by the beta. What is this called? Beta G. Okay. Beta G. And this is multiplied by the theta. And I will just put the guide that the theta is coming from. No, I don't like this one. Okay. From there, actually from, okay, theta is coming here. Okay, and what is it? 2 over S beta G times theta, and theta, which is 2 times delta over S. Yeah, Ura's gonna put you in difficult times for a while, because none of this is given. So you got to try to figure out by yourself how things come up, how things pops up. Actually, this is quite fun to figure out how the relationship is cast. And then the next step, you have 2 and 2, it turns out to be 4. This is equate to the 48 EIX over LQ delta. And then I will rearrange. We want the beta G, right? So we move everything to the other side. Oops, sorry. I will cross something out, like the delta is going to be crossed out with this delta. That makes the 2 cancel with the 48, and you have only 12 EIX left there over L cube. You have S here and S here. These two denominator will be turning back there on the left side into the numerator. S squared is equal to beta G. Okay, looks like this. This is how the beta G is derived. I put it here. See derivation below. Okay. So we clear another thing that could be frustrating to us. Not be able to figure out what and how this come from. So it has a reason, but the reason is not explained in the detail. That's it. Now it's gonna be more frustrating because I am not going to get down into detail of these things, but all the gangs, Helwig, Yura, and Franks, they are all the members at UT Austin. So, have shown for twin girders, the strong axis beta G is significant, and equation number 7 can be used even when there is more than one brace along the span. When you have the situation that we derive for the 12 EIS square over LQ is the worst case scenario already. If you look at the case where you have multiple girders like this, they are all connected together like this, you will end up with the smaller force, smaller vertical force that is acting on the girder, so that produce less effect. It used to be 2, now you have 4/3, so 4/3 is just 1.333, right? Smaller than 2. So this recommendation is going to be conservative, because you will not end up with the case that require, or the case that the BG will be you will just end up with the smaller force on the girder caused by the brace, torsional brace. And then the cross-section distortion. Okay, this is going to be a long story, and if possible, then I'm gonna put the explanation. I've looked up for a good explanation of this beta section, but it is about the distortion of the cross-section. So it talks about the parameters from your stiffener, and you can see that the parameters they are obtained from the pictures on the right hand side. Okay, so as the cross section is deformable, your beam cross section is deformable, and when you put the stiffener, it is less deformable, it is stiffer, and that will be computed and be used in the calculation of the total torsional stiffness. Okay, when full depth stiffener or connection details are used, okay, this is actually the recommendation for the calculation of the beta section. When you design, you can just opt for the full depth. It is the best. But if you cannot go for that, you come to the pictures pretty much like this one. It's not the full depth, it is just the partial stiffening effect is going on in just a part or some part, but it's not all the way extending to the top. So the calculation can be obtained, it can be done from the equation number 9. Okay, and then time flies. It is 9:20 already. And we should have enough time to cover the issue about the exam. So it hooks back to the equation number 5. It is just to make it more realistic than the original derivation. So equation number 5 for continuous bracing could be adapted for discrete torsional braces. I emphasized you already that it is originally made for the continuous torsional brace, right? by summing the stiffness of each brace and then you divide. It is as simple as that. So if it is discrete, then take the discrete spring and divide by the length, so you get the rotational spring stiffness over the length. Okay. By summing the stiffness of each brace along the span and dividing by the beam length to get an equivalent continuous brace, okay, etc., etc. And this equation is modified, so the M naught turns out to be the CB, okay, just came in place, and it adjusts the capacity. And this part on the back here, you can see that you have the BT. Okay, BT stands for the total torsional brace stiffness. So it is the sum, right, of 1 over BT equals to 1 over B section, 1 over B girder, 1 over B brace. Okay, EI, okay, over CT. And okay, I may not cover this part. This is about the cross section that is just singly symmetric. The bottom one is the doubly symmetrical cross section. We rarely bump into this situation. It is just a detail issue. And well, top flange load. Okay, no stiffener. Okay, fine. We come to this point here. So torsional brace design, and it is just coming from the equation here. So the torsional brace design comes from this point here. The required brace stiffness must be at least twice the ideal stiffness. So this is identical to the design of the lateral bracing, like the column, like the lateral bracing of the compression flange of the beam, which is the same thing. We are in the same situations as the torsional brace, which is going on in the beam. To keep the brace force small, okay, so we need the twice of the ideal stiffness. Can be obtained by rearranging equation 12, and yes, finally you end up with this. So basically you start from this equation, you square everything up, the square root is gone, you need this thing, so this goes back to that side as the minus sign going there. And then you take the CT, you throw it there, you throw this, you throw off this there, and finally you'll be ending up with the equation here. Okay, and the 2, this is the 2 times ideal brace stiffness for torsion. Just emphasize how the 2 come from. And furthermore, the force, the bracing force and bracing moment is obtained from the initial imperfection. So the way the initial imperfection is set up is affecting the bracing force, right? And set up here, the initial twist is given by 0.002, which is 1 over 500 L. This is consistent as you used to see the number here in the previous derivations. Okay, 0.002 lb over h. So you need to change from just the out of straightness to the rotation or the twisting, initial twisting. So divide by the h, which is the depth of the cross section, and that makes it the rotation or twisting. It's recommended this value is consistent with the initial lateral displacement of this used in the development of the lateral bracing requirement. So it just show that everything is consistent. Now, okay, we are in the torsional bracing design, and the equation are obtained from the part there at the top, right? So what to be number of intermediate brace along the span is given. EI, CB. Okay, we saw all this already. The reason for 2.4, we might be frustrated from wait a minute. Yeah, this is something frustrating. CEIBB, okay, is there. The CT, oh, okay, yeah, the 2.4 come from the CT being neglecting term CBMO M0, which is going to be, which will be small compared to MZR. Okay, so this is treated to be 0. Okay, so this is gone. First thing, but I should highlight it there, such that equation 13 can be simplified conservatively. Of course, the bigger the brace stiffness, the better, right? Okay. By neglecting the term, okay, and taking the maximum CT, which is 1.2 for top flange loading. So this is the worst case scenario, right? For top flange loading, it is conservative. This is conservative design. Top flange loading, which is the worst, bad handwriting here, worst case scenario. So plug in the CT being 1.2 and CB is there. Okay, so that's why from equation 13 you can come down to here, to multiply by 1.2. I can upload this version of the paper with all markings for you, so it is possible for you to just look into the explanation made in here, point by point. Okay, bracing force is obtained. Fill everything in, but you see that you have a bunch of things, because in the section B section you have the CST. Okay, this one we know already, BG already. This is in the 1/B section, so it is just a complicated issue that you have so many things, many parameters. It depends on how you furnish your cross section. Okay, and the rest is the torsional brace design example by Ashto. I'm not going to ask you to design any brace or anything in like this, like the example like this. Okay, this is just the cookbook. So if you want to cook something, you follow the step. It is the step recommended in ARSC. So this is not the course that we learn the design. We learn the behavior of the structure, and I just wish that you understand how everything behave. And once you understand this in the design, it will be automatically improved. So okay. In here, this is a list of paper that are used to constitute this given paper that we are reading. So it's gonna be quite interesting, probably in the next year, to look into the detail of this paper, these sets of paper. Maybe some explanation, in detail explanation, might be given in the other paper, but Yura doesn't want to talk too much and spend time in this paper, spend pages and lines in this paper about the explanation. So it might be found in the other paper, right? But it's going to be fun to understand every single details about how the formulas in the AISC is proposed, at what basis, what is the understanding behind each formula is very important. And most of the time, seriously, in ACI and AISC, I have seen a lot of my students just picking up the formula without understanding the formula and then just plugging in the variables. And most of the time it is incorrect. It is done incorrectly because you are trying to be like to treat the code of practice like a cookbook. So you don't read. If you don't read, or if you don't try to understand how come each individual formulas is written this way, then there is very high chance that you just pick up the values in the wrong way. And believe me, formula like this is very sensitive. You end up with something like very, very sensitive. You put something wrong in there, your design might be super dangerous. Or you feel like this is not good, you try to make it super conservative. You put the number in the like conservative manner for all parameters. Then you end up with the crazy design that you cannot make it in reality. And now you are at the point where one side is so scary, okay, because it might need quite a very small cross section in the design, whereas another side is super chubby. It is too big. Cross section is huge. It looks ridiculous. And when you are at that point, you make decision. And what should be a good number? Should you go for the conservative side? And if you don't understand the formula or how come it is, you might use the wrong formula for the wrong situation. That could be one thing. But if you by chance pick up the right formula, what would be the good number for the design? Something right at the middle, the most conservative and the least conservative, then add up and divide by 2. Is that going to work? I don't think so, right? The most conservative might be from unrealistic condition, unrealistic assumption, so that is not going to work. So I cannot, for the course of advanced steel structure, I cannot just cover everything. It is just like the RC or other courses. I think no instructor can cover every single corner in the recommendation for the design or the provision codes. But the fundamental is that when we learn the course like this, we try. I think I have been trying to drag you through the understanding of the basis of everything, from the tension member, from the compression member, right? From the beam, from the stability of the column or the bracing for column and the bracing for the beam. Along the way, we have seen the derivation from the scratch, from the fundamentals, from the ground. We do the piling work, and then we start the pile caps and columns, piers, floor, etc. So we start from the scratch like that. And I show how the starting from the scratch could be done in several things already. And we have only this many classes, like 30 classes, and totally we have 45 hours. I try to cover more, further from the video that we finish up in this course in this year. I try to cover more. But if you bump up into the situation that I do not cover yet, I have not covered yet, or I may not cover in the future, because I don't think that it is generally used for people. It might not be beneficial to, not going to benefit people in the big group. Then I might not cover, right? So, but you yourself might need to look into some specific detailing of each issue. So hopefully you know how to start from the scratch. Hopefully you know how to research and find how to start things like this, and correlates everything all the way to the code level, and you understand that how much conservative you are, right, in your design. This is so important, and it could be extended into other things in your life, for the research, for, well, life is all about the research. So I think I planned the idea, I planned the procedures for you. Hope you can apply these procedures in your everyday life in the future.